All right, so picking up where we left off, what is it today that looks very familiar on a construction site, as you might have expected, if you were watching construction on the Pyramid of Giza through that knot hole in the wood, on the shielding outside the site? Well, I really have three major components that I want to address. Obviously, everyone's going to have their ideas, and they're probably all right. We can chat about this when we meet in person, but really, when you talk about construction, things are still number one, labor intensive. Okay, when you look at the construction sites today, yes, there's equipment, there's machinery. We're building higher, we're building farther, deeper, whatever the case may be. But the majority of the work is still performed by human beings. All right, so there needs to be a trained labor force out there to be able to accomplish what we need. And never lose sight of that fact when it comes to construction methods and materials and how we do things. All right, so number one, 5,000 years later, 4,500 years later, we still rely on physical uh, labor force to do a lot of the work. Yeah, there are tools and there are things that can be done, but we still need, for the most part, personnel to operate those tools and to do some of the work that there's not necessarily equipment to do. All right, so number one, and then number two, equipment is used. All right, just like we described, building of the pyramids, there were probably rollers and pulley systems and things that were used to leverage what we know about physics and engineering to assist the labor force in doing what they need to do. And that's really what we have equipment for today. Much of the same stuff, and we still do rig things like pulleys and other kind of systems, and then fancy pulleys like a crane. So there's still plenty of ingenuity and use of equipment to help the labor force. And then number three is to perform construction. What do you need? You need the materials to build what you're going to build. And it may have been, some kind of stone or rock that was used to build the pyramids, and then whatever your building materials and methods are today, you still need to purchase, acquire, deliver, and install all the materials that you need to build what's on your drawings. So, you know, typical construction, labor, equipment, and materials, that's what drives your costs. That's what drives, pretty much your plans if you're looking at it from a cost perspective. And, it basically drives everything up through construction and the built product. So those are the three major items, and you may have had others, and I definitely have other opinions on that of what looked the same and what doesn't. But really, everything kind of revolves around those three major topics, and not a lot has changed when you think about it in 4,500 years. So just wanted to put things in perspective. So the changes in construction and the materials and the methods are not that fast. So things we discuss in this class probably will carry through the next 10 to 15 years. Of course, there are innovations on a daily basis, but the general concepts have remained the same throughout time and will remain the same forward. So if you understand and grasp the basics, you'll be in a good position to continue on and then understand all of the changes that happen afterwards. All right, so there's other pyramids that are still standing today, like the bent one. I'm not sure if this was particularly designed like this, or was there a revision about halfway through when they realized they didn't have the material to make it all the way up to where they wanted to, that they increased the angle on it so that they reached the top point of the pyramid a little faster, and then didn't need as much material to still make an enclosed pyramid. So feel free to research that one. I just thought it was kind of interesting that we have the bent pyramid there. Was it by design, or was this a budget or material saving issue, or was it an error? Who knows? All right, so I want to talk a little more. You saw the graphic on the buildings. The Eiffel Tower was once one of the largest structures in the world, and it's all steel construction, very similar to the same elements and theories that we use today to build skyscrapers. And again, that was 120, 125 years ago, and things haven't changed too much. When you look at older construction, not only in the Eiffel Tower, but many of the steel structures around the city, bridges, whatever it may be, older buildings, when you go onto the interiors and you look at the steel connections, they used rivets. All right, so hot rivets to penetrate through the steel and connect two pieces together. Nowadays we use pre-drilled holes or holes drilled in the field and then bolted connections that are torqued to maintain those connections. So the steel itself, may have changed slightly. There'll be different alloys, different strengths, but more or less the fabrication of steel is still the same thing. Mixing the different ingredients, getting it to a certain heat, molding it, cooling it, quenching it. All the same processes basically as the steel that was built back in the day. So we take a look at this, and really, there was a couple of innovations here, and the biggest thing was basically two big ones was that this began the concept of prefabrication, meaning making some of the elements off-site, putting them together, and delivering them somewhat assembled already, so that there was less on-site assembly, or you assembled larger pieces so that construction at the site was quicker. And that carries through to a lot of the construction we do today. We prefabricate a lot of materials and get them to the site so that the actual field work and time at the site is limited, or is as brief as possible, because we know how hard it is to work in a city environment and get deliveries and get through traffic. So the more you can put together off-site and bring in an assembled piece already and just fit it in, it's much easier to construct on the site. Number two, they used a hydraulic jacking system. All right, so that's a very important concept when we talk about high-rise construction soon, not only for the construction, but also for the use of the crane. That's how some of these cranes on the sides of buildings get propped up to the next level, and we're going to talk about that as well. And in general, jacking is used in a lot of situations, not only to support buildings adjacent to construction, but to also lift bridges to replace bearings and perform a lot of other work. So that kind of methodology and method of construction is still used today. And then lastly, it's kind of linked to that one, is that crawler cranes were used to erect a lot of the steel members. So cranes that were mobile and not just limited to overhead, gantry, or stationary were used here. So there were a lot of great innovations used not only in the design here, but in the construction aspect as well. So that's, anytime you see a new largest tower or, one of the highest ones in the world, it's likely that there's some innovation there to make that happen. So this was, an amazing project. It was built in about 2 years and only used a labor force of about 250 people. So using the assistance of crawling cranes, jacking, prefabrication, they were able to cut down on the time and amount of labor that was necessary to build this thing. And lastly, just a note there, to accommodate the workforce so they wouldn't have to spend time coming up and coming down off the project site or off the highest levels to take care of themselves. When you look at the tower, there's a second level there. There was a cafe. Well, we like to call it a cafe, but there was probably just lunch brought up to the guys there that were working on it so that they wouldn't have to take time to come back down, which also probably wasn't the safest at that point. So you're limiting their exposure to risk, and you're also saving time so that your manpower and labor force can continue working. So, innovations that we use today, at a construction site. If you don't want labor force spending too much time, they have their half-hour union break or whatever it may be. They have what they call the roach coaches, or those mobile carts, similar to what any of us would eat on the city street, one of those hot dog vendors or a mobile home that's converted to a little restaurant. So to get the food to the labor force so that, they're able to keep on working. So, a lot of innovations. All right, so here this is just a couple of glimpses of the construction in progress to see how things were put together and the time frame it took. Again, it was just over 2 years. Foundation was 5 months basically, and then the tower construction was about 21 months. So that's a pretty speedy project considering the height and the amount of steel back in 1889. Just locally, we talk about the Empire State Building as well. If you want to do a little research on that, you take a look at how quickly that was built. Back in the 1930s, I think, when it was constructed. and you always get that famous photo of the ironworker crew sitting on a beam that's being erected, basically, that's held by a crane and being lifted, and they're sitting there with their lunch boxes balancing on the beam there. So, wouldn't meet today's OSHA standards, but it helped speed construction back in the day. All right, so that's just a little introduction to some structural steel and some construction methods. And then now we're going to go into the organization of what you see in a typical design and construction project, so you understand where decisions flow from, what the project teams look like, and how things get done on the paperwork side to lead to the construction. And so typically there's got to be an owner leading your project, providing the funding, and basically making the decisions as to what the design should look like, or aesthetic decisions. There's different levels of involvement from the owner. They can either be totally hands-off and say, here's my budget, create a design and build it, or they can be very specific. I want this, 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 and this, and then I will pay whatever it is. So, it varies, but generally the owner will have someone who's technically savvy on either the engineering side or the construction side, as a construction manager in the process, from the beginning, acting as their project manager. And then they will hold contracts in a typical project organization with all the different entities. They'll all be separate contracts held with the owner. It would be an architect, a contractor, possibly a geotechnical engineer or engineering team, an expediter to work on permits, which we'll talk about in a little while, someone to handle the environmental aspects, and then coordinate utilities. So some of these things could be lumped under one thing. There could be a general engineering box that handles environmental, utilities, geotech, and then there would be a separate contract with an architect, contractor, and expediter. The expediter could also potentially work for the contractor, or a CM if a CM is hired early on. So there's a number of ways to organize a project team on the site. This is one of the typical org charts, just to give you an idea of all the things that are involved in getting a project off the ground and running. In a design organization, again, the owner could hold this contract with one particular organization, like a large company that has all of these other elements underneath them and all these other skill sets. Or some owners, if they're more involved and want to handle things themselves and coordinate and everything, will have separate contracts with each of these firms. So generally, in my experience, it would be the owner holding the design with one prime engineering firm, and it would be up to that engineering firm to hold subcontracts with all the other expertise and specialists that they may not have in-house. So for instance, if your main contractor on the design side is an architect, they may have structural engineers, mechanical engineers as subcontractors, and vice versa. If you have an engineer as your main, they may have an architect and other subcontractors under them. But typically the owner will have a contract with the designer or multiple designers to get the design work complete. Once you get into the construction process, I also teach a Intro to Construction Project Management course at NYU, and I go into great detail on the construction process. And really the takeaway I want to leave you with here, you can look at the detail of this and understand all of the various intricacies and what you need to get the construction process going. But even prior to the construction process, there's at least, on a typical project, 15 steps to get to that you saw partially in the last slide. Permits, environmental aspects, coordination with utilities, all these various steps that you have to get through before you physically get to construction. And then once you get to construction, it's a tiered process. Again, you need if it's not a green site or what they call a virgin site that hasn't been touched before, you obviously have to take care of what was there before, whether that's excavating material or demolishing an pre-existing structure, getting it down to where you need to do your own work, and then building a new from there. So, plenty of steps into going through this. Construction works intertwined with the engineering. So when you look above there, You see the mobilization, demolition, and then what you have to do: excavation, layout, footings, columns, and then on up through the structure, MEP, etc. But that there's a big interaction with the designer through all of those steps. You have to submit shop drawings, you have to submit materials for approval, so that all gets reviewed on the design side, approved, and then sent back to you for you to fabricate and build. Uh, and in the meantime, you're tracking all your subs work, you're scheduling your subs work, you have to take into account safety considerations, you're tracking schedules, you're tracking budgets, making sure that anything that needs to be ordered that's a long lead item is prioritized early on and submitted for approval so you can get those underway and fabricated, such as major components like structural steel, mechanical elements of the building that have long lead times, fans, vents, generators, switch gears, you name it. There's a lot of things that you have to consider that needs to get in process and fabrication early, so that when you're ready to construct that element of the work, it's there and delivered on site, approved and ready to be installed. So we look around, where NYU is, and whether it's the downtown campus, midtown campus, or in Brooklyn, we're surrounded by high rises. We're surrounded by big, massive construction. Now, you can't have that everywhere. There were certain things that basically facilitated New York as an area for good high-rise construction. And take a few minutes to see if you can rack your brains and think of a couple of reasons why New York City would fit the bill as a good place to build high-rises. And we'll pick up the next section of the lecture with the answers to that. And all right, let's pick up here with why New York City ended up being a good place to construct high-rise buildings. And when I first thought about the answers to this, the first thing that popped up the top of my head was the fact that New York, at least for high-rises, as buildings got bigger and bigger, ended up being an ideal place because it has rock foundation. The stability of the Manhattan schist. It's a very strong rock that you can drive piles and drill foundations into that can support very large weight and has high capacity. So from a geotechnical standpoint in the foundations, remember that diagram that without good footing, you really can't have a good building. So New York ended up being really ideal in the geological side and geotechnical side to be able to build big buildings and to support that kind of weight. So that's really what's my number one thought. But when I took a look at things back through history, we realized that there are a number of reasons why New York was a great place to construct high-rise buildings. With the expense of property in New York City, right? The property is really the same cost whether you build a small 2-story building or a 100-story building beneath it. Of course, depending on the location, has a lot to do with the price of the property. But once you have the property, you can make greater use of that by building a high-rise. You get more tenants, whether it's commercial or residential. You can fit a lot more into that space. So if you build higher, you can get more income investment. But New York was also a hotbed and a center for invention that made there were a number of engineering feats that were accomplished locally in New Jersey and New York that enabled New York to be a good place for high-rise buildings, and specifically elevator construction and safety devices for elevators were Otis was a great pioneer of that, located nearby. Edison in New Jersey was big on electricity, and so you need to get lighting up to higher floors of the building. You can't risk having candles everywhere to burn down a building. So once we started building higher and we had electricity, we had the ability to light it. We had the ability to run devices like elevators and escalators to get higher up into the building so you wouldn't have to walk. Again, location of the rock. Rock is high here. You know, as you look across at the Palisades, across the Hudson, you realize that the rock is actually rising as you get through the city. So in most places in the city, it's either at the surface or very near to the surface. You don't need to excavate to get to a very strong foundation in most cases, and sometimes you even have to blast just to be able to get a basement or a foundation in to get through the rock. So it's a it's a great geological, geotechnical area for high-rise buildings. We had water here, so you could provide for a lot. We had the infrastructure to support having a lot of people in one place whenever you start building, large residents and having a higher density of population in an area. We had access to waterways that could make quick deliveries of material, being surrounded by rivers on both sides of the island of Manhattan. So there were a lot of factors that went into why high-rise construction really took off here in New York. And if you look around at other cities like Chicago, Philly, Boston, they had very similar pathways to becoming big cities. They all had a lot of things in common with New York City. So access to water, delivery, materials, not having ridiculously inclement weather, not prone to having hurricanes and tornadoes, things that could be devastating to, or earthquakes, things that could really be devastating to high-rise buildings. So New York became a great place to build a high-rise building, and it still is today. And as you can see from looking around at the skyline, you notice a new building every few months just making its way up to the skyline. All right, so again, like I said, infrastructure is definitely a necessity when building high-rise buildings. You need to have the infrastructure to support it, meaning plumbing, heating. You need, gas supply, oil supply. You need the electricity. You need water in and out, clean water in, wastewater out. So, having all that infrastructure in place is essential. So how do we govern buildings? How do we know what we have to build to? What tells us that we need fire escapes? What tells us that we need multiple access? What tells us that we can't have certain things in certain types of buildings or certain zones? So, what New York City did and what most, organized cities do is they have codes and permits. And this could be local, they could be statewide, but New York City has very specific local codes and permitting requirements that kind of dictate what can be built where and what needs to be included to make it a legal building. Right, so the reason why we have codes and permits is to make sure that whatever is being built meets a certain level of safety for the users or the public. Like again, I said, whether it's commercial or residential, certain things need to be in place to make it safe. Just as an example, you can't have a high-rise building without fireproofing and firefighting. You need a sprinkler system. You need fire stops in a building. And all of this is kind of learned over time. There were a number of incidences and disasters in larger buildings early on in the turn of the century that led to having these codes and summaries. Fires spread quickly through buildings, and many people lost their lives. So we realized the materials that used in buildings, have to have some kind of fireproofing to them to keep it from being engulfed in flames so quickly. Then as we became more cognizant of the fact that we could put in sprinklers and had the ability and technology to do so, that became part of the code as it went on. So codes are a living body. They change as technology changes. They change as new things are found out, and sometimes they change because they're spurred into change by something like a disaster. So, we have a number of these codes and zoning requirements basically to protect the public. right, so they protect the public from injury. They try to prevent potential failures, particularly catastrophic ones that could lead to the loss of many lives, and protect general unsafe conditions from those who use the buildings. So, again, we have a number of codes and a number of zoning issues here in New York, or requirements and codes that protect those who live and work in these buildings. And again, like I said, typically there are it's almost a disaster or a really bad incident that spurns major changes in codes. The Great Chicago Fire of 1871 that wiped out like much of the city. There's the rumor that it was or might be historical fact now that a cow tipped over a lantern in a barn that started the fire, and it's just it spread so quickly that they were unable to stop it. The great Triangle Fire disaster here in New York City, which was basically a sweatshop that got quickly got engulfed in flame, and then because the emergency exits were locked and closed, people couldn't escape. So there were that contributed to code changes requiring a number of egress or ways to exit a building, so that there wasn't only one or two exits that you could go by. Typically in the U.S., we go by the International Building Code, or IBC. And again, like I said, codes are living bodies. The IBC updates every 3 years, so the most recent one was only about a year ago, so we should expect another one at the end of 2017. And again, it gets updated based on new materials, new technologies, and then obviously to be included in the code, it has to be a material or technology that's proven, been tested, certified, and to make it into the list of approved materials for construction. And again, just to give you a representative example of requirements, and the fact that anytime there is a change, there is a time frame that's given to allow existing buildings, or buildings that are being built from this point on, to accommodate to those changes. Because obviously, if there's a change in code, a building that was built in 1910 may not be in compliance with that. We can't say, well, just tear the whole building down and let's go. So it's usually a very fair process. It gives you some time to adapt to it, to install whatever is needed to get up to speed on the code. So, again, they're flexible in that manner, but again, you have to eventually meet that requirement to maintain the ability to use that location. Okay, again, just additional examples. You can go ahead and read these, for your benefit, just to take a look at what governs a lot of the building and building retrofits here in New York. Okay, and any time that you're doing construction, you're required to have a permit. And obtaining a permit from the Department of Buildings is a way to ensure that you have what's required to safely construct whatever you're looking to build, and that it meets codes and regulations. So typically, to obtain a permit, you need to provide the architectural drawings or whatever plans you have to show that, hey, this is what we're building. So typically, architect, engineer, they get the sign and seal drawings together, and an expediter will work with the owner to try to get these over to Department of Buildings and get concurrence so that they can get the signed permit in place. Oops, sorry. And again, the permits are in place. They get approved. We've all walked around the construction sites and seen that big clear glass over about 20 sheets of paper with Department of Building logos on it and stuff. Those are the permits, and it's a requirement of the permit to post them in a visible place, so people know what's going on there. And also have a number of signs, I'm sure you've seen, that says, if there is an unsafe condition, call here's the owner, here's the architect's name, those are all requirements of the permit. So those are all posted to meet the permit requirements. If an inspection is made there by the city agency and they don't see that these things are in place, they can retract your permit. So they want to make sure that if anything is on that site that's not being done properly or safely, and someone in the public wants to report it or workers want to report it, that all the information is visibly displayed so that they can easily be contacted. Permits are in place to make sure that the building works that are planned are in accordance with the code. Obviously there's a review for code compliance, and that the contractor is preparing the site using means and methods that are also according to a code. So it's not just the design plans; it's the methods and the ways that the work is being completed. And of course, we're going to cover that a little bit more in each of the sections as we go through specific topics. All right, and then lastly, that the contractor is not impeding the public. So they need permits if they need to close the parking lane on a road to facilitate the contract. They need to get permits from DOT for that. There's a number of different permits that need to be addressed or issued depending on what your needs are on the project. Right, and building permits can vary, and they range. Everything from just doing little renovations on a one-family home to building a new high-rise. Right, so there's a number of different building types, building application, and permit types. And then if you work in that industry and work with an expediter or are an expediter or architect, you become very familiar with these quickly as they're a day-to-day part of your operations. But typically there's new buildings, various alteration types, in different categories depending on how extensive those alterations are, and then PA public assembly for spaces that could hold more than 75 people. So again, you would apply for the permit type that relates to your building. So again, obtaining permits are Right, so obtaining a permit's not always an easy thing, and it's like everything else in our business, requires a step-by-step process. Requirements for permits are pretty much left to the localities because each location has different issues and things that they have to deal with. Obviously in New York, with all the infrastructure that's here and adjacent buildings and roadways and things like that, there's a number of more requirements here than maybe in another location. But anyway, it's set kind of locally and it changes locally. So depending on where you work, you'll get a little bit more familiar with what the requirements are in those locations. But generally, it requires you to submit signed and sealed drawings from the engineer or architect of record. They have to be registered in the state that the work's taking place in. They're also the permits are signed by owners of the properties. Another couple of pertinent bullets here. Permits are not cheap. You generally have to pay for them in most jurisdictions, and they're issued for a limited period of time. Importantly, here in New York, the expiration date for that permit can be linked to the workers' comp or your insurance policy dates, so that no work can take place past those dates unless you provide an updated insurance certificate prior to when that one lapses. So again, that has to be done before you lapse so you can continue construction and you can continue using that facility and working there. And you may need the expediter to step in and, once you get that updated cert, go through the motions of getting the updated permit, which will have a reflected date, of the new insurance certificate. So again, permits displayed in a public place, and that's a requirement here in New York City. And that, should an inspector from the city show up, they need to have access to all the approved drawings, so you need a full set always kept on site. Right. Zoning is another aspect of permitting and another way to keep the public protected. It only allows certain construction types and permit types within certain areas. And part of that is that, so if you live in a neighborhood of one-family homes, someone can't buy a property on that the one-family home next to you, knock it down and build a 60-story apartment building right next to you. So areas are zoned to kind of maintain the kind of area that you're in, if it's industrial, if it's commercial, if it's private and residential. That way, the types of construction are limited to meet what's in those zoning requirements. In the city, a unique aspect are air rights, basically how high you can build within each of the zones and the building type that you're going for. And there's there's a calculation based on floor area ratio that you have to run to know what you can get. If you want to go beyond that number, you can also apply for a waiver, and there's ways to get that done as well. So we're going to cover this when we get into construction a little bit more, but this is just a typical spreadsheet showing floor area calculation. And again, like I said, a unique aspect of New York City here is the air rights. A number of the buildings, they're not built up to the maximum air rights or height that they can get to. So when that happens, builders and developers can purchase the air rights for that building and add to the building, and then they'll have to go into a permit for alterations, and depending on the type, secure that permit. So it usually comes at a cost to purchase those air rights. That's unique to high-rise construction, particularly here in New York City. Just an example of a zoning map. As you can see on the right-hand side of this, there's notations there: R for residential, C for commercial, M for manufacturing. So it kind of indicates what can be built in that general areas of the map. You see here. So when you go in for that permit, depending on your address, they'll check, make sure that what you're looking to build or what you're looking to alter or renovate fits within the zoning of that building. And if not, you get your permit denied or rejected. All right, so I'm going to end this section here and pick up with testing and quality control on the next section of this lecture. All right, class, now we're going to begin what is the last segment of lecture number 1. So hopefully you've gotten used to using the online tools and have been able to access all of the lectures. So we're going to go through some quality assurance, a couple of tidbits and then get onto the assignment or the first homework assignment of the course, which will be due at the next class. You can either hand it in person or submit it online. I prefer you submit it online so I have record of on-time submission, and that way you get it to me as soon as it's complete. We don't have to print paper out, and you can just send it through email to rmm299@nyu.edu. So before I get into the quality control portion of this, again, an interesting just additional information on air rights. Really, the idea is that with the air rights comes the ability to build up higher. It's basically the use of developmental rights. If you haven't maxed out on a particular building, you can either build higher on that building, add additional floors, and renovate that way. Or there's a way to actually purchase those air rights to use on an adjacent building. There's a number of different ways you can get around these developmental rights to work with it. So there's zoning lot mergers, there's transfers of the developmental rights, and again, you just have to look into your zoning, see if you're not in the you haven't maxed out the developmental rights on those or the development rights on those properties, and then figure out how you can build higher. Or if you have maxed them out, is there an adjacent property that hasn't, that you can purchase from and use towards yours? So it's a very intricate process. Those who work in the city have to become very familiar with it, especially those who are on the investment side of new construction and renovations. So just a very, very interesting process around high-rise buildings that's unique to high-rise buildings. I just wanted to let you fill you in on that information as well. So quality control. All right, it's great to have on paper a set of plans that says this concrete is going to be 4,000 pounds per square inch, and that'll be strong enough to hold up a 20-story building, and that it won't crack, it won't fail, it won't fatigue for 100 years, and that'll be a great material. So with almost every material, you as a construction manager or an engineer are going to be looking to see that, or an owner, are going to be looking to see that whatever you get, whatever is installed in the field, meets what's in the plans and specs, so that you're getting a quality product. And how do you do that? Basically, it's testing. How do you make sure that something is what they say it is? And there's a number of different tests, and there's tests that can be applied to almost any material. Generally, the requirements for the materials and any of the testing requirements will be found in the specifications for the project. Oh, and sorry, for those of you who don't know, what you see there is basically testing of concrete. They have a cylinder there, a test cylinder that was made out of a batch of concrete that was used in a building. It's labeled to identify where it came from or what load it was in. And then what they do is they basically perform a lab compression test, and as soon as that thing fractures, they note how it fractured, when it fractured, and what the load was on it. So if this was supposed to be a 4,000 psi concrete mix, and it breaks under 4,000 psi, then you might have a problem. Typically, there's a couple of samples taken, 3 cylinders made, and they'll take the average of the break of those 3 cylinders. So if you just happen to obtain, a section of the mix that maybe had slightly higher water content than it should, or because of where the mix was or the time it was taken, it was a little bit different. They won't let one low result be a rejection factor. But if you have 3 cylinders and all 3 react the same way, then you had a bad load of concrete, and it may not have been mixed properly. It may have been in the truck too long and may have had too many revolutions in the truck, so things started to segregate. There's a number of reasons why something could fail, but you can't always spot that with the naked eye, and you can't always spot it with the testing that takes place at the field, which can only confirm really temperature, slump, and air content of the concrete. You can review the delivery tickets to make sure that you got the right mix and the materials that went into the mix, but really you need some kind of test at the end to prove it, and typically it's done by a compression test, as you see here. And that's what you would do for concrete. Now, there's 20, 50, 100 different other materials used in your building, what do you have to do for those? So basically, testing is that systematic way to assure quality construction. All right, there really is no ifs, ands, and buts about it. Testing can sometimes take place at the site, like I mentioned before, slump and air and temperature testing. Testing can take place at the plant to know that the materials they say that are going in there meet the criteria for those materials, whether it's the sand, whether it's the stone size, which is called the aggregate, or the amount of water that's included in the mix. All of that can be measured and tested at the site, at the mix site, the batch plant. And then there's the testing that takes place afterwards, after the concrete is cured, after it's set, that you take and you break those test cylinders. Right, so criteria is established again in the construction documents, usually the specifications for each of the items, and those can differ slightly depending on the agencies or the owners and user groups, but generally they all kind of fall within the same kind of pattern and requirements. Why do we need testing? All right, so again, it would be great if we could take everyone's word that things are delivered, built, manufactured, provided, mixed exactly as they should be, using proper techniques, using clean materials, using the proper materials. But it doesn't always happen, and it's not always intentional. Things happen, and it's not because of any malicious intent on anyone's part, but sometimes things just don't meet up to spec. And it could be, like I said, it could be a hot day out there. You lose some of your water in transit. The load sits a little longer than it should, and then the next thing you know, you have concrete that's a little low on water, which leads to lower strengths, and then you get a bad break. So that concrete has to be pulled out and rejected, and then basically taken out from where it was placed. So testing is needed on a number of fronts, but it's really to, again, much like zoning. And much like permit requirements, we test to protect public safety. Again, testing is something that probably came about because of a disaster of some kind, or an error, a mission, something that happened that required and made someone think, hey, you know what? We need to start testing this material to make sure that it meets the codes and requirements and meets the need for the project. And much like concrete, again, I said there's a number of other materials. Connections need to be tested, whether they're bolted or welded. Bolted connections, we test the actual bolts for strength, and then we also test the installation of the bolt to make sure that it's at the proper torques, so that it's properly fastened and tightened. Welds can be tested in a number of ways: visual exams, non-destructive testing, X-rays, and destructive testing of welds to make sure that that you have the the proper strength of material there and the proper adhesion to hold together what you're trying to hold together. All right, so everything on down from curtain wall assemblies, steel, pipe piles, timber piles, piping get pressure tested. The flow tests for ducts. Life safety systems, meaning alarms, sprinklers, things like that get tested to make sure that they can stop the spread of fire or any of that. And then performance testing to make sure that things operate as they should, whether it's a motor, whether it's a switch gear, whether it's an elevator or escalator. There's a number of tests that are performed not only on the individual components of those things, but again, once everything's installed and in place, that it can operate as they say it's going to operate, so you know that not only is it safe, but you also got the quality of product that you're paying for. If the elevator is rated for 1,600 pounds and through testing of the cables, you find out that your cables aren't sufficient and they don't meet the testing requirements, then you need new cables, or the whole elevator isn't rated for that weight. So again, it goes from various components, and then it goes for testing as a full assembly later on down the line most of the time. So getting familiar with your contract, the plans and the specifications are very important, particularly up front, because you want to, and when I say up front, I mean at the time of bid, because you want to make sure you have considered these items when you're pricing out your job, so you can not only build a successful project, but a profitable one as well. Again, why do we need testing? Testing is really done for public safety, and that all leads from meeting the design requirements, the code requirements, again, getting the product that you paid for, safe building practices, protecting the lives of the people who will be using that for that next X amount of years. And then it also allows you to figure out a solution. So, let's say you've placed that concrete floor and you have, bad test results. What can we do? Short of just tearing down the whole thing, are there ways to retrofit that so that you can keep that concrete in place and still get the strength that you need? Or do you basically just go and tear out that concrete and have to replace it and re-pour it? But what it does is it gives you that option to be able to figure out what to do, rather just saying, oh man, we have this floor that's not supported, or this concrete pour didn't meet strength. It gives you that ability to adjust during construction and figure out a way to keep on moving and keep building that project. Right, and then lastly, things are designed to last a certain amount of time, and they'll only last that long if they meet all of the requirements that are stated in the specifications. So if something's meant to last 20 years and they say it needs to have X amount of strength, if it doesn't have that strength, it won't last those 20 years that it was designed for. So we test materials and do quality assurance and control testing to also ensure that longevity. Because especially when you're investing in something like a high-rise building, you're not intending to have to tear it down or lose it in 10 years because of faulty construction. You want this thing to last your lifetime, 50, 100 years or longer. Again, there are testing procedures established for just about everything, and there are different organizations and entities that have done a lot of research and have gone into great detail into describing how specific tests need to be done. And again, the testing isn't worth, anything to you if the procedures aren't followed per the test requirements. We've done, as part of my role in construction management and engineering, we've done audits of facilities that perform independent testing, and we find flaws in some of the testing sometimes in that they're not actually following the procedures as they're supposed to by code. So the results that come from not following the procedures aren't worth anything. So you have to follow each step by step to the T to make sure that the results you get are adequate and legitimate. So again, just looking at the flow chart here, there's an established standard. A testing lab will perform tests to those standards. Again, they have to do it exactly as per those standards and use the right standards for the particular material or procedure. So you get the results of that, and if the results are good, that work is approved, and if the results aren't good, either that material is rejected if it's not something that's installed already, or if it's installed, you need to figure out a remedial or a corrective action to repair that deficiency. And again, there's, you can go on and on naming how many different kind of building materials there are, and there are almost an equal amount of organizations that go into figuring out how to test all these materials. For concrete's the ACI, or American Concrete Institute. Here in the U.S., for precast concrete's a different organization, PCI. So basically, there's codes for just about everything. You'll see UL listings on electrical equipment, AWS for welding. So it goes on and on. Underwriters Lab is UL. And you may have noticed that as a stamp on or a sticker on even things like three-prong plugs that go into your outlets. So that'll be everywhere. There's testing standards for all the materials. Basically everything that's used, especially on government projects, gets scrutinized to ensure that they are meeting the standards, and the materials that are placed and installed and constructed are meeting all the plans and specs. So just a moment here, you can go on and look through this at your leisure. It's basically just the type of field tests that go on for a variety of things. Number 3 foundations, they do pile load tests to ensure that the pipes, or not only pipe piles, but whatever kind of piles, drill shaft, timber piles, whatever is installed can meet the load requirements. And there's different type of load testing that can take place depending on what kind of pile you're using. Concrete there, you'll see some of the terms that I've mentioned earlier. Compressive strength, slump temperature, concrete design mix, sieve analysis, air content, core samples. We basically covered most of those when we saw the compression testing cylinder and sample there at the beginning of this portion of the lecture. So just about everything goes through some kind of testing. Steel gets tested from when it's fabricated. The alloys and the materials have to go through testing to make sure that they're the right composition, that they have the right chemical makeup to give you the strength steel you need. Then when it's molded and in place, we test the actual product of the steel to make sure it's got the right strength. And then that steel, when it gets put in place, whether it's bolted, welded, etc., those connections get tested to make sure they're of the right meet the requirements and standards that you need to meet. And this gets carried on through almost any piece of equipment, any piece of material that you deal with in a building: HVAC, electrical piping, roofing materials, curtain walls. And what I like to point out there is in curtain walls, you see mock-up in laboratory. A lot of this material has to go through what we call off-site testing, or testing at the manufacturer or fabrication facility, so that you make sure that those items will meet the specifications when they get to your project. Otherwise, you tell them, you reject them on the spot there at the fabricators and wait till they can make something that meets your requirements. So that's usually a long lead item. You want that to take place early so that if there are any issues with this material, you have the opportunity to try to refabricate it or get another component in place and still not lose time in your construction schedule. So this is a really interesting diagram or figure that you see here, how smart structures work. Construction is getting more and more complicated now, and it's because buildings are starting to catch up with the technology of the times. And it's not just buildings, it's also this kind of technology is being used in bridges and tunnels, not only to monitor how well they're performing, but to also monitor them for potential defects so they can be identified quickly and remediated to prevent any kind of disaster in the future. Technology, we have to keep up with technology, and buildings are keeping up with technology. They're becoming what we call smart buildings. They have sensors in the buildings that not only monitor for things like earthquakes, so that they can resist an earthquake by engaging hydraulic dampers, but they're also using to manage the building itself. Temperature sensors on the outside that control your HVAC systems so that you're not expending tons of energy cooling a building when it's cool enough outside to vent in some outdoor air, filter it, and move it into the interior sections rather than having to force cool what's already on the inside. It automatically operates your louvers and dampers to control the airflow, then how much exterior air will come in or how much recycled interior air you're cooling, and the same for the heating. So they're building information systems that feed these things back. The computer takes care of the adjustments, and a lot of it's automated where you don't have to do too much. You just make sure your settings are correct, and then those things take care of themselves and monitor themselves. So, just amazing. You see building fit outs today, and basically sensors are all over the place, and it's something you have to be very cognizant of in the construction to ensure that these are, placed in the right place. They have tolerances, that they're installed properly, and some of it's very delicate. So that's just another added layer of complexity when it comes to building and constructing something properly. But what it does in the long run is it helps the longevity of the building. It helps the ease of management of the building, and it helps your structure and the personnel. The structure survive longer, and the personnel inside be more comfortable. So it's a big selling point to a lot of commercial buildings that they have these smart systems that they can use that to sell potential clients and purchasers of space for future tenants that, hey, we've got all this stuff in place. This is going to be the best building for you to bring your company of 10 floors worth of personnel. So it's all being woven right into the fabric of construction now. So the following are some general good practice points that my colleague Rich Lembeck, who's taught this course for many years, and is an expert in construction management and teaching it. He's got this list of good practices, and I really enjoyed reading through this list and think it's excellent to pass on. So I kept this. Number one in construction is never believe anything someone tells you until you can prove it, and that's basically that quality assurance testing. You like to believe that all the concrete that you get from your supplier is up to snuff, and there are no issues with it. But if you basically take everyone at their word, you're eventually going to get burned at some point. And again, like I said, not through any malicious intent, but there could just be poor materials that got incorporated into something, and you don't want to be the person that has to deal with that. So, always confirm things. Be observant at your construction sites. Make sure you know what's going on around you in all your surroundings, not just in construction for materials' sake and proper practice, but for safety. And we're going to have a lecture a couple of weeks that really delves into site safety and things you need to do to be aware of your surroundings. Written documentation is always the best. We'll talk a little bit about claims and change orders and things like that. But word of mouth is not something that can be used in court of law or not easily used in the court if things come down to a claim situation. So having written correspondence and notes are very important in the business we work in. Try to keep written correspondence simple and to the point. Don't to keep it simple, stupid, KISS method. That I find that to be completely true. If you start getting too complicated and say too much or write too much, you might write something that you didn't really intend to. So just keep things simple. Get your point across and move on. Always try to understand not everyone's an expert in all aspects of construction. But someone is obviously going to be stronger in electrical, but may not have the same grasp on civil or structural. So I'm aware that I'm not an expert in everything, and I think everyone who works in the construction field realizes that they don't know everything about everything, and that's why there are so many different kinds of engineering or construction. There's disciplines for electrical, mechanical, and this isn't only in the engineering field. This is also in the labor field. People who do work on mechanical components are not the same people that will work on electrical components or structural erection. It's a different labor crew. It's a different force, a different union who are trained completely differently. So if you don't understand it, feel free to ask questions, and that's something I greatly encourage in the in-person classes. That if raise your hand. Let me know if you have a question and we'll address it. And then obviously any of these online lectures, if you have a question, you can always email me, send me an email, say, hey, I didn't quite understand this, or, I had this experience. What do you think of that? I'll be responding to emails all throughout the course. All right. And then, as was shown in that slide of new technology, and as kind of shown through the history of construction, there's always going to be changes and updates. And that's why codes change every 3 years, and why keeping up to date and continuing education is always required, particularly to keep licensure if you're an engineer. But always, trying to learn what's new. It's really important. So, keeping up with technical magazines, keeping up on top of the current issues, reading publications in building construction. You never know what might give you that idea that'll be the big cost-saving thing or the big thing that wins you that next contract with the private developer. You want to stay ahead of the curve and keep up with all this. So I'm going to leave you with this slide and the next slide. Really, you can take a look through them, but they're all just little tidbits and general good practice recommendations, and I like most of them and agree with them. So, take a look through there. We got one more page of them. All right, when meeting with large groups of people, always prepare an agenda, always take meeting minutes, try to keep everyone focused on certain topics so you can get through it. When you have a lot of people involved, it's often difficult. It's like corralling the herd of cows. You can't get them all going in the same direction, so you need some tools to try to keep them focused in the same direction, and that's what your agenda's for. And lastly, this last one, it's a procedure in most of what we do in engineering or construction in terms of quality assurance. But having someone review your work, those of you who work in the industry and have seen a set of plans will always see that there's about 3 levels of who drafted it, who designed it, who checked it, and then someone who signed it, who has the authority over all 3 of those other, the checker, the designer, the drafter. So a number of eyes have looked at the same thing, and it's just another few layers to make sure that there aren't errors in what's submitted and what's signed off on. So it always pays if you have the time, and we know time is always of the essence, and the schedule is so important. But really, if you have the opportunity when you've written something up, whether it's a letter, whether it's a proposal, to always have another set of eyes look at it. Because sometimes when you look at the same thing over and over again, you can't catch the mistakes, you can't catch the errors because you read what you want to read instead of what's actually there. So getting that second set of eyes is always recommended. All right, so and we're here to learn. Obviously, we're all continuing on. Most of you are here for trying to earn a master's degree, but whatever the reasons are, you're here to learn, and learning's not something that stops just because you stop taking a course. Or you're not in school at the time. Learning is just an everyday thing, and something that I generally support and try to do every day is try to learn something new every day. And then lastly, like I do, I truly enjoy what I do at work. So I hope I'm doing it well, and I think really the key to being good at what you're doing is to enjoy what you're doing. And obviously, I think everyone in this course enjoys what they're doing in the construction field. Otherwise, they wouldn't be seeking to further their education in it. All right, and lastly, for this class, I think it was a great first class and a very broad introduction to many of the topics that we're covering. I hope it's engaged you and it's gotten you interested into what's going to come in the future couple of weeks. We have a really good course here that really covers a lot of topics in depth, and will give you a great introduction to everything in materials and methods of construction of the typical materials used in a building. And let's start off with this homework. All right, I'll leave it up there for a couple minutes. You can either print it out or screenshot this and print it out, or just leave it up on your screen and pause so you have it. And basically, it's due next week. At the next lecture, or prior to the next lecture if you want to send it in via email. All right, so it's just basically a historical study and comparison on 4 well-known buildings here in New York City. Why was it constructed? Do a little research as to who the primary engineer was. Take a look at the duration of the construction. A lot of this is easy to find on the internet. Just provide some references as to where you're getting your information. So if I see something that's not correct, I'll know where it came from. Take a look and see if you can find out what the initial construction costs and estimates of what something like that would take today. Do your best to find all this information. Give me a general outline of what kind of structure it was. Was it structural steel, concrete, wood? What kind of connections were used? If you can find out some information on the foundations, just do your best to find out what you can. Obviously, you'll get full credit if you can find everything, but if you make a great effort at it and 1 or 2 of these details are lacking, that won't be held against you as long as you put in the effort to to try to find out. So take a look at these, try to answer them as best you can, submit them again via email rmm299@nyu.edu, or you can bring them to class and hand them in person. Have a great week, and I will see you at the next class, lecture number 2. Thanks very much.